Welcome back to The Deep Dive, the show that takes complex infrastructure, slices it up, and hopefully rebends it into something intuitive and entirely understandable.
Today we are wrestling with what is probably the single most frustrating and I think fascinating topic in cloud-native computing, Kubernetes networking.
Oh, definitely.
If you're preparing for a job interview, or if you're dealing with those intermittent 503 errors that just drive you crazy, or really if you're just trying to understand what runs the modern internet, this is your deep dive.
We've all been there. It's late, you're on call, and something is broken. You sit down, you open your terminal, and you type the simplest command imaginable. curl api.coolapp.com
Good tip.
millis musers.
The classic test.
And it just hangs,
Yeah.
or it fails. And if you just stop and think about it for a second, you realize that humble little packet of data is about to embark on this dizzying multi-layered journey.
It really is a journey. It
Yeah.
has to move from the outside world, from your laptop, all the way down to a specific socket inside a specific container, and it's probably bouncing across multiple servers in the process.
And that journey is what we're demystifying today, right?
That's the plan. We are taking the, let's face it, immense complexity of Kubernetes networking and framing it not as a maze, but as 5 very precise, very modular layers.
Okay, 5 layers.
5 layers. Each one solves a distinct problem, and importantly, each one provides a crucial failure point or an observability hook. If you can map the packet's path through these 5 stops, you transition from just being a K8s user to being a K8s master.
I like that. 5 layers, 5 specific challenges that have to be overcome for my curl command to get a 200 OK.
Exactly.
So let's lay out the mental map. What are the 5 stops on this journey we're building for you?
Okay, so stop 1, layer 1 is the ingress controller. Think of it as the external gatekeeper.
Right, the front door.
Then layer 2 is the service. This is the stable directory for all your ephemeral, constantly changing pods.
The fan book.
The phone book, exactly. Layer 3 is kubeproxy. This is the kernel translator and the rule writer. This is where the magic happens.
This sounds like the really deep technical part.
It gets pretty low level, yeah. Then layer 4 is the CNI, or the network fabric. These are the physical roads that make sure a packet can actually get from one node to another.
And finally,
Layer 5 is the pod network namespace itself, the application's final isolated destination, the private office where the work gets done.
okay, this map is already helping.
And we aren't just tracing the path, we're going to detail the mechanics at each stop. We need to understand the security rules, the load balancing decisions, the address translation, and the specific artifacts, the logs, the kernel rules, the packet headers that you need to check when things inevitably go wrong.
All right, let's do it. Let's unpack this, starting at the perimeter. Let's hit layer 1.
The gatekeeper.
Our journey begins right where the request enters the cluster network boundary.
Yeah.
So layer 1, you called it the gatekeeper. And in Kubernetes, that role is played by the ingress controller.
Exactly. Think of the ingress controller as the HTTP receptionist for your entire cluster. It is fundamentally a layer 7, an application layer traffic manager.
Okay, layer 7. That's a key distinction. It's not just routing packets based on IP addresses.
No, not at all. It's much smarter than that. It handles things like hostname routing, sending api.coolapp.com to one service and website.coolapp.com to another. It does path matching. And often it handles cryptographic functions like TLS.
So if the receptionist doesn't approve my ID, meaning the host header in my HTTP request doesn't match a rule, my request is just terminated.
It's terminated right there. It never even sees the internal services. It's a hard stop.
You've isolated 2 crucial components here that I think people often get confused about.
Yeah.
The rules themselves versus the thing that enforces the rules.
That's right. And it's a critical separation. First, you have the rules. That's the declarative ingress resource. It's the YAML manifest you write that says, if someone asks for api.coolapp.com your malwares, please send them to the user service.
That's my intent.
That's your intent. Second, you have the enforcement mechanism, the actual running ingress controller pods. These are typically built on really high-performance proxies. You've heard of them, NGINX, a proxy, or Envoy.
And that controller is just sitting there in a loop watching for new ingress resources to appear.
It's a classic Kubernetes control loop. It continuously reads those declarative rules and programs the proxy configuration in real time. A new ingress object appears, the controller sees it, and it reconfigures NGINX on the fly.
And the choice of that controller, That matters a lot, doesn't it?
Hmm.
Because different vendors, like Nginx versus Envoy, they handle that reloading very differently.
Oh, it matters immensely. This can introduce subtle latency when you're scaling up or changing services. For example, some older NGINX ingress controllers might require a full configuration reload to pick up a new rule.
Which could mean dropping a few connections, right?
It could, even if it's just for a fraction of a second, where something like Envoy, which is used in a lot of modern service meshes or controllers like Contour, it uses this highly dynamic API called XDS to update its routes instantly without dropping a single connection.
That's a subtle, but wow, a massive performance difference at scale.
It really is.
Yeah.
Now, how does the outside world even discover this receptionist? This is where your Kubernetes cluster has to touch the cloud provider infrastructure.
Right, because the Ingress controller is just a pod. It has some internal cluster IP. My laptop can't reach that directly.
Correct. So most commonly, the ingress controller pods are fronted by a Kubernetes service of type load balancer.
And that's a magic word in Kubernetes.
It is. It's a special keyword that instructs your cloud provider, AWS, Azure, GCP, whoever, to go and provision an external, typically layer 4, network load balancer and point all of its traffic toward your controller pods.
So the cloud gives me a public IP address, and that IP points to my Ingress pods.
That's the most common path. Alternatively, say in a bare metal setup or a really high density private cloud, you might deploy the controller as a daemon set.
So one pod on every single node.
On every single node, ensuring it's running locally, and then you'd point some centralized external hardware or software load balancer to the specific node port used by that daemon set. The common thread is there must be a public physical IP address managed externally that gets traffic to the ingress controller.
Okay, and since we're at layer 7, let's talk security. This is the natural place for things like TLS termination and web application firewalls, right?
Absolutely. TLS, or Transport Layer Security, is critical here. The controller has to terminate TLS.
Meaning it decrypts the request.
It has to decrypt it specifically so it can inspect the HTTP headers, the host name, which it gets from a TLS feature called SNI, and the path. This requires the controller to hold the private keys and certificates.
And those are stored in Kubernetes secrets.
Stored in Kubernetes secrets, which the controller pod has permission to read.
And what happens if that process fails?
Yeah.
If the certificate is wrong?
You get an immediate high visibility failure. If the certificate is expired, or if the host name you requested doesn't match the certificate the controller provides, your browser or your curl client throws an immediate fatal TLS handshake error.
So you don't even get to the point of sending the actual HTTP request.
Never. The conversation ends before it begins. It's a
Yeah.
very clear signal.
You also mentioned way integration. How does a web application firewall fit into this layer 1 picture?
So Away also operates at layer 7. It inspects the content of the request, but it does this after TLS termination. It's looking for patterns that indicate attacks, things like SQL injection, cross-site scripting, the usual suspects.
So it's another layer of inspection.
It's an additional validation layer. When you integrate it with the ingress controller, which is usually done as an add-on or maybe a sidecar proxy, the WAFAX is a security check before the request is routed internally. It's your first and strongest line of defense.
Okay, so if the receptionist sees suspicious behavior, the request is blocked right there. It never touches the actual application.
Exactly, long before it gets anywhere near your application code.
Let's talk about the common failure modes here and how to diagnose them effectively. This is where people get stuck.
Right. The failures here are usually pretty binary. It's either a complete connection refusal because of a TLS issue, or it's a routing failure. And the classic routing failure is the 404 not found.
Okay, a 404. If I get a 404, how do I know if the ingress controller never even received my packet, or if it received it but just couldn't match the rule? That's a really key distinction.
That is the key distinction. If the ingress controller never receives the packet, you're not going to get a 404. You're going to get a connection timeout or maybe a connection reset. That points to a problem at a lower layer, maybe your cloud load balancer or the network fabric.
But a 404 is different.
A 404 is a layer 7 response. It's a polite no. It means controller successfully accepted the TCP connection, it successfully terminated TLS, it read your HTTP request headers, the host, the path, the method. It looked at its internal routing table that it built from all the ingress resources.
And it found nothing.
And it found no matching backend service.
So in a weird way, receiving a 404 means layer 1 is actually working as intended, but my configuration is wrong.
Precisely. The receptionist is doing their job perfectly. You just ask for an office that doesn't exist. The evidence is clear. Check your declarative rules. Run kubectl, get ingresso YAML. If the host or the path is wrong in that file, that's your fix.
Now, to eliminate variables and diagnose layer 1 specifically, there's this synthetic test you mentioned, which is in our sources. This is so valuable.
It is, because DNS can really obscure the actual problem. Your DNS could be pointing to the wrong IP, for example. You need a way to bypass the DNS lookup while still tricking the ingress controller into thinking the request came from the correct domain.
The command for that is?
The command is curl-vk first flag resolve-api.cuelap.com.443.lbip https://api.cuelap.com users.
Okay, let's break that down. The resolve flag is the magic here.
It's pure magic. It tells curl, hey, for this one command only, anytime you need to connect to api.cuelap.com on port 443, don't use DNS. Go directly to this IP address, which is the public IP of your cloud load balancer.
Well, it forces the connection directly to the load balancer, but, and this is the important part, it still sends the correct api.cuelap.com host name in the TLS SNI header and the HTTP host header.
Exactly. So the controller thinks it's a legitimate request for that domain. If this command fails with a TLS error or a 404, with 100% certainty that the problem is specifically your layer 1 configuration, your certificates, your secrets, your routing rules, and it has nothing to do with your public DNS setup.
Mastering that single command is a huge step in structured debugging.
It really is. It isolates layer 1 from the entire dependency chain that comes before it.
Okay, so the request successfully navigated the gatekeeper. The ingress controller read the rules. It knows exactly where to send the traffic, let's say to the data processing service. This transition moves us from the edge inside the cluster to layer 2, the stable directory.
If layer 1 was the HTTP receptionist, layer 2 is the phone book entry.
I like that analogy.
The fundamental problem that the Kubernetes service object solves is the ephemeral nature of pods. In a dynamic cloud-native environment, pods are cattle, not pets. They are scaled up, they crash, they get moved to different nodes.
And every time that happens, they get a new IP address.
A completely new, unpredictable IP address. And yet, everything inside the cluster, from the ingress controller to other microservices, needs a static, reliable way to address that functional group of pods.
And that's the service object.
Correct. The service object provides that stability. It assigns a stable network identity, the cluster IP, which never changes for the entire lifetime of that service. When the ingress controller forwards the request, it's not targeting a specific pod IP. It's targeting this stable cluster IP.
So it's the crucial mechanism for service discovery inside the cluster network.
It's the core of in-cluster service discovery, yes.
So how does this static, stable address connect to the actual constantly shifting set of pod IPs? And where does that link happen?
That is the core mechanism, and it's managed by the Kubernetes control plane. The service object, in its YAML, defines a spec.selector.
Which is just a label query.
It's just a set of labels.
Well.
For example, app.dataProcessor. The Kubernetes controller manager is constantly running this query against all the running pods in the cluster.
And the result of that query that gets stored somewhere else.
Exactly. Kubernetes populates these auxiliary objects called endpoints, or in newer versions, more efficiently, endpoint slices.
Okay, what's the difference?
Endpoint slices are just a more scalable version of endpoints. With the original endpoints object, if you had a service with 10,000 pods, you had one giant endpoints object with 10,000 entries. Every time one pod was added or removed, you had to update that huge object, which caused a lot of churn in the control plane. Endpoint slices break it up. So you might have 100 endpoint slices, each with 100 pod IPs. Now, if one pod changes, you only have to update one small object. It's much more efficient.
But the function is the same. These objects contain the definitive, constantly updated list of live, healthy pod IPs and the ports they expose.
The ground truth: if 5 pods match the selector and are considered ready, the endpoint slice will list those 5 specific IP addresses. And this list of real destinations is what the layer 3 components, what we're about to talk about, the kube proxy, actually use for forwarding traffic.
It's important to clarify the different service types, too, because they dictate how that stable cluster IP is exposed.
Right. There are 3 primary types you'll encounter. The first is cluster IP. This is the default, and it's internal only.
So this is for when service A needs to talk to service B inside the cluster.
Exactly. It's stable, but it's completely unreachable from outside the cluster network fabric.
Okay, what's next?
The second type is node port. This one is a bit more direct. It exposes the service on a specific fixed port across every single node's physical IP address.
So if I have a 100-node cluster, I can hit port 300,007 on any of those 100 nodes and get to my service.
Correct. This is often used when you need a predictable port exposed on the host itself, but it kind of bypasses the sophisticated load balancing of layer 1 and is generally less common in large production systems. It can be a security concern, too.
And the third type is the one we already mentioned.
Right, load balancer. As we discussed, this integrates with the cloud provider to provision an external L4 load balancer that targets the nodes and routes traffic to the services pods.
Okay, let's get into the failure modes here. Unlike the really clear L7 errors like a 404 or a TLS error at layer 1, layer 2 failures feel different. They're often silent and lead to these really frustrating timeouts.
We call this the silent failure. And the biggest red flag, the number one thing to check, is when the service exists and the cluster IP is correctly targetable, but when you run kubectl get endpoints,
Yeah.
the list is empty.
The phone book entry exists, but the office building is empty. Nobody's home.
Nobody is home, and 99% of the time this is due to a simple label mismatch. The label defined in the service selector, say app data processor, doesn't exactly match the label set on the running pods. Maybe there was a typo.
Data processor instead of data processor.
I've spent hours on that exact typo. The controller manager sees 0 matches, so the endpoint slice is empty. Traffic hits the stable cluster IP, but there are no backend destinations, so the packet usually just gets dropped at layer 3 when the kernel attempts to forward it, and you get a timeout.
So a quick check at kubectl get endpoints OYAML, followed by comparing the selector field in the service manifest against the labels in the pod manifest, is the essential debugging step here.
It's step 1 for any connection timed out error inside the cluster.
What's the second major failure at this layer?
The second one is the stale endpoint. This happens if a pod suddenly crashes, maybe it gets killed out of memory, but the control plane hasn't yet removed its IP from the endpoint slice.
There's a delay.
There's a slight reconciliation delay. So for a brief window, traffic continues to be sent to that dead IP. This is what causes those maddening intermittent connection drops, or 503 errors. One request works, the next one fails, the next one works again.
Because it depends on which endpoint the load balancer happens to pick.
Exactly. This really highlights the distributed state problem, doesn't it? The service definition is stable and logical, but the endpoint list reflects the dynamic, volatile reality of the cluster. That list is the bridge between the logical network of layer 2 and the physical forwarding system of layer 3.
All right. The request is now targeting the stable cluster IP. But, as we established, this cluster IP is a fiction. It's not a real thing. It's not assigned to any physical network interface on any node. It is a magical virtual IP. This brings us to layer 3, which you said is the most technically complex translation step.
Yeah.
This is handled by the kube proxy and the node's kernel.
This is the leap from a logical address to a physical address. Our mental model here is the rule writer, rule executor.
Okay, I like that. Who's the writer and who's the executor?
Kube proxy is the rule writer. It's a daemon that runs on every node, and its whole job is to constantly monitor the API server for changes to those layer 2 endpoint slices. The Linux kernel, using its powerful packet filtering mechanisms, is the rule executor.
So when a packet that's destined for that fictional cluster IP arrives at a node, the kernel has to somehow intercept it and transparently rewrite the destination to a real pod IP from the endpoints list. Where does this interception actually happen?
It's intercepted using the kernel's network stack hooks. Specifically, if we're talking Iptable's terminology, this happens at the pre-routing chain in the NAT table.
Pre-routing, so that means it happens before the kernel even makes its main routing decision.
Exactly. It's one of the very first things that happens. The kernel sees a packet destined for, say, 10.96.0.5, recognizes that IP as part of a rule written by kube proxy, and performs a destination network address translation, or DNAT.
So the packet arrives destined for 10.96.0.5.80, and the kernel just silently rewrites it to, say, 10.244.315.8080, which is a real pod, and then just lets it proceed as if that was the original destination all along.
That's exactly how DNAT works. The source IP address is preserved, but the destination is changed under the hood. The application that sent the packet has no idea this translation ever occurred.
It's completely transparent.
Completely. Now let's expand on the two primary modes kubeproxy uses to write these kernel rules.
Okay, let's start with the original one, iptables mode.
Right. Iptables mode relies on writing these extensive sequential chains of NAT rules. For every single service and for every single endpoint for that service, kubeproxy writes rules that, in effect, randomly select an available pod IP from the endpoint list.
It sounds complicated, a lot of rules.
It is a lot of rules,
Yeah.
and this works reliably, but it has a significant performance drawback. When you have hundreds or thousands of services, the kernel has to traverse these long sequential chains of iptables rules for every single packet that comes through.
So the more services I have, the longer the list the kernel has to check for every packet.
Exactly. That adds latency and CPU overhead, especially under high load. It doesn't scale well.
And this is why IPVS was introduced, right? To get past that sequential traversal problem.
Yes, IPVS mode is used for high-performance scenarios. IPVS stands for IP Virtual Server, and it's a dedicated load balancing framework that's been in the Linux kernel for a very long time. It's battle-tested.
And how is it different?
Instead of long chains of sequential rules, IPVS uses highly optimized hashing tables to look up the destination pod IP.
So it's a direct lookup instead of a linear serve.
It's a hash table. It's a constant time lookup, which is a huge performance gain. IPVS also supports more sophisticated stateful load balancing algorithms beyond the simple random selection in iptables mode.
Like what?
Well, algorithms like least connections, where it sends the new request to the pod with the fewest active connections, or weighted round robin. It allows for much finer control over how traffic is distributed among the backend pods. The end result is far lower CPU utilization and reduced latency when you start scaling your services massively.
So regardless of the mechanism, whether it's iptables or IPVS, let's talk about that load balancing decision. How does the kernel translator choose which pod IP to forward to when there are, say, 5 pods in the endpoint slice?
In the older iptables mode, the selection is generally random across the available pods. In IPVS mode, as I said, you can configure much more deterministic policies. The key is that this decision, this kernel-level load balancing, happens entirely transparently at layer 3 based on the rules kubeproxy generated.
Let's revisit that critical failure story that makes this whole abstract layer so concrete, the kubeproxy crash.
Right. This is a textbook example of a control plane dependency causing a data plane freeze. The story was about these intermittent 500 errors that were isolated to just one node in a large cluster.
Frustrating to debug, I'm sure.
Extremely. The investigation finally showed that the kubeproxy pod on that one node, let's call it node X, had crashed. It hit an out-of-memory event, and it had failed to restart cleanly.
So the problem was the network, it wasn't the application, it wasn't even the endpoint list in the API server. All of that looked healthy.
Exactly. The root cause was that the rule writer was dead. But the kernel, the rule executor, it doesn't know that. It was still happily forwarding packets based on the last known good set of rules that kubeproxy had installed maybe hours ago.
Oh, wow. So if a pod had died, or a new one was added after kubeproxy crashed.
The kernel rules on that node were stale. They were out of date. Traffic was still being DNA'd to dead pod IPs, resulting in silent packet drops and application timeouts, but only for traffic that happened to land on node X.
That's a powerful point because it forces us to decouple our layer 3 checks from what the API server tells us. The kernel's reality can be hours old.
The only way to see the kernel's reality is to query it directly on the node. The debugging signal for layer 3 is absolutely crucial. First, check the health of the kubeproxy pod, but then you have to shell into the node and inspect the forwarding tables yourself.
Using what commands?
You'd run iptables water more nettt nat nash n, or if you're running in IPVS mode, ipvsetm nash ln. If you see stale or incorrect pod IPs in the output of those commands, you've found your layer 3 failure point.
The packet has been successfully rewritten. It arrived at node A, the kernel did its DNet magic, and it changed the destination from the cluster IP to a real pod IP, an IP that lives on node B. The packet now must traverse the physical network. This is layer 4, the network fabric, the domain of the container network interface, or CNI.
Layer 4 is the physical roads and toll gates. The CNI's primary responsibility is simple to state but complex to execute. It has to ensure L3 reachability between any two pods in the cluster, regardless of which node they live on. It provides the mechanism for internode communication.
And there are several major CNI implementations, right? And the choice you make here defines your entire network topology and performance profile.
It's a fundamental architectural decision.
Let's contrast them, starting with the overlay model. This one is arguably the easiest to deploy, but maybe the hardest to debug.
I think that's fair. Overlay networks, like the popular CNI flannel, create a virtual network on top of your existing host network. They rely on encapsulation, typically using a technology called VXLAN.
Encapsulation. So it's like putting a packet inside another packet.
That's a perfect way to think of it. If Node A wants to send traffic to a pod on Node B, Node A takes the original IP packet and it wraps it inside a larger UDP packet. That new outer packet is destined for the physical IP address of Node B.
So the original IP packet just becomes the payload inside a new transport packet.
Precisely. There's a VXLAN header that gets added by a kernel module called the VTE, the Virtual Tunnel Endpoint. That header identifies which virtual network the packet belongs to. When the big packet arrives at Node B, its VTE strips off the VXLAN and UDP headers and presents the clean original IP packet to the kernel for local delivery to the destination pod.
Okay, but that encapsulation,
It costs us something.
in terms of bandwidth and potential MTU headaches.
It does. It absolutely does. The source material notes a 20 to 50 byte header overhead for every single packet. That doesn't sound like much, but it can become significant at high throughput.
And the MTU issue can be a nightmare.
It's excruciating to debug. If you're tunneling over a physical network with a standard MTU of 1,500 bytes, you must reduce the effective MTU inside your pod network namespace to account for the size of that encapsulation header. If you don't, large packets get fragmented or just silently dropped.
So what's the alternative to tunneling everything?
The alternative is using routed CNIs, and the most common example here is Calico. These CNIs use the host network directly. Instead of wrapping packets, Calico programs the routing tables on the host machines themselves, often using the Border Gateway Protocol or BGP.
BGP, that's a massive topic. That's what ISPs use to run the internet. How is it used inside a Kubernetes cluster?
It's the same protocol, just on a much smaller scale. Imagine your nodes are like little postal carriers. Instead of tunneling mail in a big envelope, which is what VXLAN does, Calico has each node act as a carrier, advertising the specific subnets, the pod IP ranges, that it's responsible for directly to the central network router, or even to the other nodes.
So it's building a real routing topology.
A real L3 routing topology. This requires managing things like autonomous system numbers and maintaining reliable BGP peering relationships between all the nodes.
Wait, so if I'm on node A and I'm using Calico, I can send a packet directly to a pod on node B without any tunneling. Isn't that technically a security risk? The pod IPs are now routable on my main network.
It's not necessarily a security risk, but it is a trade-off. It's complexity for performance. You completely eliminate the encapsulation overhead, which is fantastic for speed and throughput. But you introduce the complexity of managing a large meshed BGP network.
And if that BGP network has a problem?
A BGP flap, a temporary disconnection or instability in the route advertisements, can instantly cause large-scale reachability failures that are much, much harder to diagnose than a simple VXLAN tunnel being down. You trade an encapsulation problem for a routing reliability problem.
Then finally, we have to touch on the newest approach, eBPF-based CNIs, like Cilium.
eBPF is a radical shift in how this is all done. It uses the extended Berkeley pack filter to run these little sandbox programs inside the kernel itself.
So the logic runs in the kernel, not in user space.
Exactly. This allows networking and security logic to be applied directly in the kernel's fast path, often bypassing the traditional Linux networking stack entirely, including iptables and the generic routing mechanisms. This can result in unprecedented performance. Some eBPF CNIs even eliminate the need for kube proxy altogether because the eBPF programs handle the service translation and load balancing themselves.
Wow. Okay, so beyond just transporting the packet, layer 4 is also where this crucial security function lives. The toll gates, as you call them, or network policies.
Right. Network policies provide microsegmentation. They operate at L3, L4, allowing you to write declarative rules based on pod labels that define which pods are allowed to talk to which other pods.
So even if the plumbing, the VXLAN tunnel, or the BGP route allows the packet to reach the destination pod's node, a network policy can still enforce a deny rule.
Precisely. The CNI implementation, whether it's Calico or Cilium or another CNI that supports them, is responsible for translating those declarative network policies into actual firewall rules, usually iptables rules or eBPF maps on the local node.
And if a policy denies ingress traffic from my source pod,
the packet is silently dropped at the kernel level by the CNI's firewall rule. This is a super common source of confusing timeouts because the application never even sees the connection attempt. Everything else looks perfect, but the connection just hangs.
which is why packet captures are so vital at this layer. You have to know where to run your TCP dump.
It's all about location. If you run TCP dump on the main node interface when you're using an overlay network like Flannel, you will see the large VXLAN wrapped UDP packets. That confirms layer 4 is encapsulating and routing correctly.
But if I run it inside the pod's network namespace,
You must see the clean, decrypted, original IP packet. If you see the clean packet inside the pod but the application isn't responding, the problem is further up the stack at layer 5. But if you see the VXLAN blob on the node, but you see nothing inside the pod, the problem is the CNI on that destination node failing to decapsulate or deliver the traffic, a clear layer 4 failure.
we have made it. The packet has been DNA'd, it's been transported across the CNI fabric, and it has been successfully delivered by the node's kernel to its final recipient. This is layer 5, the isolated network namespace of the pod.
This is the private office. All the complex infrastructure layers, 1 through 4, have done their job perfectly. Success now rests entirely on the application that's running inside the container. Is the process actually alive? Is it listening on the right address? Is it overwhelmed with work?
And the physical isolation here is really crucial to understand. Every pod gets its own dedicated, isolated network environment.
That's achieved using some really cool Linux networking primitives. The pod gets its own network namespace, which means it has its own local host interface, its own 127.0.1, its own routing table, its own interfaces.
It thinks it's a real machine.
It thinks it's a tiny little virtual machine, and its connectivity to the outside world is provided by a VETH pair. Think of it as a virtual Ethernet cable. One end is plugged into the pod's namespace, and the other end is hooked into the node's main CNI bridge or routing table. The pod's IP is assigned to the interface inside that namespace.
I remember spending, I'm not kidding, 6 hours one night chasing a timeout, only to realize the application was binding to 127.0.0.1. That feels like a frustrating rite of passage for new KACE users, and it has to be the #1 layer 5 failure.
It is the most common and the most subtle application error that masquerades as an infrastructure failure. If your application code binds its listening socket only to 127.0.0.1, the loopback address, it's telling the kernel, I will only accept connections that originate from processes inside the same pod.
It's listening, but only to itself.
Only to itself. So when the packet arrives via the CNI addressed to the real pod IP, like 10.244.3.15, the application's binding just ignores it, and the kernel sends back a connection refused error.
So the golden rule for any containerized application is that it must bind to 0.0.0.
0.0.0, which is a special address that tells it to listen on all available network interfaces, ensuring it receives traffic that's routed via the main pod IP.
Okay, beyond that classic binding issue, what other application failures do we see at this layer?
Well, sometimes you see internal container firewall rules that inadvertently block traffic, but more often it's resource related. If the application experiences memory saturation or high CPU load, it might be running, but it simply cannot accept and process new incoming connections fast enough.
So the TCP listener backlog fills up.
The backlog fills up and the kernel starts dropping connections. To the outside observer, it looks exactly like a network failure, but it is, in fact, a layer 5 performance bottleneck.
When we suspect the application, how do we confirm it's actually listening without having to, disrupt the running container?
We need to peer inside that isolated network namespace, and there's a specific command for that. kubectl exec -podname ssltnp. What is that doing? It runs the SS or socket statistics utility inside the pod. The flags tell it to show all listening TCP-BRI sockets, show the numeric ports, N, and show the process that owns the socket. You are looking for a listening TCP socket on your expected port, and you need to confirm that your application process is the one bound to it.
And if I don't see my app there, or if I see it's bound only to 127.0.0.1, that's my definitive layer 5 answer.
That's your smoking gun. The problem is inside the pod.
Finally, we got to circle back to layer 2 here and discuss the critical role of liveness and readiness probes, because they really bridge layers 2 and 5.
This is such a crucial concept. Liveness and readiness probes determine the pod's lifecycle status in Kubernetes. A liveness probe checks if the process is, well, alive. Is it running, or has it crashed or deadlocked? If that probe fails, Kubernetes takes a drastic step. It restarts the container.
It assumes the app is unrecoverable.
Right. But a readiness probe is more subtle. It checks if the process is ready to receive traffic. Is the database connection pool warmed up? Are all the initialization routines complete? Is it not currently overwhelmed?
And if the readiness probe fails?
If the readiness probe fails, the running pod's IP address is immediately and automatically removed from the endpoint slices at layer 2.
Ah, okay.
The process is still running. Layer 5 is technically okay, but Kubernetes marks it as unreachable for new traffic. This prevents Layer 3 from forwarding traffic to an application that is temporarily unable to serve requests. It's a clean way to signal temporary unavailability.
So a readiness probe failure effectively solves that layer 2 stale endpoint problem we talked about earlier, but it does it gracefully by communicating application state back up the stack.
It connects application health directly to the routing infrastructure. It's the application raising its hand and saying, hey, I'm alive, but please hold my mail for a minute.
That makes so much sense.
So we've successfully traced that single curl request through the ingress, the service directory, the kernel translator, the CNI fabric, and finally into the application. The real mastery of Kubernetes networking, I think, lies not just in knowing those 5 layers, but in understanding how they interact under the banners of observability, security, and performance.
Let's start with observability across hops. We know there are 5 stops on this journey. How do we instrument them to track a single request all the way through?
This requires comprehensive distributed tracing. You have to inject and propagate a unique identifier like an XRequest ID header, starting at the very beginning at layer 1, your ingress controller.
And that ID has to be passed along at every step.
It has to be passed through the application logic at layer 5, and ideally it should be logged by the CNI plane at layer 4 if it supports it, which is something you see more in service mesh environments.
Because if the request fails 5 layers deep, we need that one ID to link the ingress access log, the application trace, and any intermediate proxy logs all together into a single story.
And your metrics have to follow this same path. Instead of just measuring end-to-end latency, you should instrument your system to capture latency histograms across each hop.
So measure the ingress processing time separately from the application processing time.
Exactly. Measure layer 1 time, layer 3 translation time, and layer 5 application time. If your total latency suddenly spikes from 100 milliseconds to 500 milliseconds, your hop metrics will immediately pinpoint whether the application added 400 meters of delay, or if the kernel forwarding at layer 3 or the network fabric at layer 4 suddenly became the bottleneck.
We talked about packet captures earlier. Let's structure that knowledge based on the layers we've defined.
Right. For debugging layer 4, the CNI, remember the key difference. If you run TCP dump on the node's physical interface, you are observing the physical road. If you're using an overlay network, you will see VXLAN headers.
And seeing them is a good thing.
Seeing them confirms layer 4 is doing its job of encapsulation. Then you run TCP dump inside the pod's network namespace. This is observing layer 5's input. You must see the clean original packet here. A mismatch between these 2 capture points immediately isolates the CNI's VTX key or routing function as the problem.
Next, let's summarize security based on our 5 layers. It's not just one thing.
No, it's defense in depth. Security is layered. At layer 1, we establish you have TLS termination and potentially a way for rate limiting at your ingress. The first level of internal segmentation happens at layer 2 with RBAC, role-based access control, which controls who can define and modify services and endpoints.
That's control plane security, preventing someone from accidentally or maliciously rerouting traffic.
Right. But the real data plane security, the packet level security, starts at layer 4.
With network policies.
Yes, layer 4 is where network policies live, providing the microsegmentation that restricts pod-to-pod communication. This is what prevents lateral movement in case one of your applications is breached. It acts as a firewall inside your cluster fabric.
And you can take it even further with a service mesh.
You can. If you use a service mesh, you introduce another powerful layer of security at layer 5 using mutual TLS, MTLS, via sidecar proxies. This encrypts traffic even between pods running on the very same node, ensuring a strong layer 7 identity validation that's completely independent of the underlying CNI.
Finally, let's consolidate our understanding of performance trade-offs. This is the ultimate consequence of choosing specific implementations at layers 3 and 4.
The performance battleground is really between the rule writer at layer 3 and the fabric at layer 4. In layer 3, the choice between itables and IPVS defines your rule lookup efficiency. As we noted, the cost of that sequential traversal in itables grows linearly with your service count, while IPVS uses constant time hashing lookups, offering significant CPU relief at scale.
And in layer 4, it's all about the encapsulation tax.
The overlay cost versus the routed speed. Overlay networks like VXLAN add header overhead and potential MTU issues, but they are simpler to deploy on almost any underlying network. Routed networks using BGP offer cleaner, faster packets, but they introduce the control plane complexity of managing routing protocols. The choice is always complexity versus throughput.
This leads perfectly into this deeper analysis of the two dominant approaches to advanced networking today: the service mesh sidecar versus the eBPF data plane.
This is where modern Kubernetes networking mastery really emerges. In the traditional service mesh sidecar model, an Envoy proxy container sits inside every single pod right next to your application.
And all traffic, both ingress and egress, has to pass through this sidecar at layer 5.
All of it. The benefit, of course, is that the sidecar provides incredibly rich Layer 7 control, policy enforcement, MTLS, observability.
But you pay for it.
You pay the latency penalty. Every single request now involves an extra hop into the sidecar proxy, an extra context switch between kernel and user space, and an extra process running, which substantially increases CPU consumption and reduces throughput. Benchmarks often show a 5 to 10 millisecond latency increase per hop, which is completely unacceptable for ultra-low latency applications.
But the alternative, using eBPF-based CNIs like Cilium, it fundamentally changes the architecture.
eBPF cuts that sidecar out of the hot data path entirely. Instead of routing traffic through a separate user space proxy, eBPF programs handle Layer 4 and even a lot of Layer 7 policy enforcement directly within the kernel space attached to the network interfaces.
So the performance is drastically higher because we're eliminating the context switching and the extra hop latency.
You collapse Layer 3, Layer 4, and much of the Layer 5 security and policy layer into one highly optimized in-kernel fast path. The downside, however, is that while eBPF is incredibly powerful, it is kernel dependent. You lose some of the flexibility and language-agnostic visibility that a user space sidecar can provide.
So it's a trade-off: unparalleled speed and efficiency versus the flexibility and mature L7 features of a dedicated service mesh proxy.
For ultra-high-performance clusters, eBPF is becoming the inevitable path.
This synthesis really shows that the 5 layers are not isolated. The choice you make at layer 4 fundamentally impacts the performance ceiling and the security model you can implement at layer 5.
It turns the maze into a map, and that map now contains actionable steps. Let's formalize that into the practical debugging checklist for you, the learner.
Okay. When that curl command fails, avoid the panic button. Follow these steps sequentially. Number 1.
Step 1. Layer 1, outside ingress check. Start with that synthetic test we gave you, curl-vk resolve domain.443.lbip https.domain path. This eliminates all external dependencies. If that fails, check your ingress controller logs for 404s or TLS errors.
Step 2.
Step 2. Layer 2, service endpoints check. Verify kubectl get SBC endpoint slices. Is the endpoint list for your service empty? If it is, fix the label selector mismatch. Is the service type correct?
Step 3. If layer 2 looks good.
Step 3. Layer 3. Kube proxy kernel rules check. Check the health of the kube proxy pod on the relevant node. Then shell into the node and verify the kernel's reality. iptables-tnot-eln or IPv6-eln. Are the pod IPs listed and they're up to date and pointing to live destinations? Step 4. Step 4. Layer 4, CNI status check. Verify the health and status of your CNI daemon set. If you're using a routed network, check your BGP peers. For overlay networks, double-check your MTU settings and VTP health.
And step 5, the final destination.
Step 5, Layer 5, pod application check. Once you've confirmed connectivity to the node, execute inside the pod. Run ssdal-oltnp to confirm the application is bound to 0.0.0 and listening on the correct port. Then check the application logs for any internal errors or resource starvation.
And what if all 5 of those steps show green?
Only then should you assume a security layer problem. Scrutinize your network policy objects and perform those targeted TCP dump captures both inside and outside the pod to confirm the packet isn't being silently dropped by a firewall rule somewhere.
That's a structured, repeatable methodology that turns a frustrating mystery into a logical diagnosis process. That was a complete trace. We realized that Kubernetes networking isn't magically complex, but it is systematically modular. We've identified the 5 specific problems that are solved by the 5 specific layers, from the ingress controller's L7 rules all the way down to the final application socket binding.
The required mental shift for mastery is to view your network traffic not as some abstract concept, but as an observable physical entity that you can track across discrete physical and virtual boundaries. To really solidify this knowledge, we have a challenge for you, the learner. Go beyond just observing and start intentionally manipulating the system.
Okay, we challenge you to practice 3 crucial mental and technical tasks.
First, map a new service completely. Choose a service in your own environment, trace its path, and for each of the 5 layers we discussed, document the specific command output or log artifact that confirms that layer is functioning correctly for that specific request. Write it down.
Second, reproduce a failure mode. Don't just read about it. Set up a small lab environment, a mini cube or K3's cluster will do, and intentionally simulate that kube proxy crash. You can do it by setting its memory limits dangerously low. Watch the kernel rules freeze, and then observe the silent traffic drops that are confined only to that single node.
This transforms the dependency lesson from a story into a practical, felt experience.
And finally,
Measure. Deploy a simple echo service using 3 different layer 3 and 4 configurations. One using standard iptables, one using IPVS, and if you're feeling ambitious, one utilizing an eBPF-based CNI like Cilium. Then, use load testing tools to measure the difference in latency histograms and CPU utilization across all 3 setups.
because only by measuring those real-world performance trade-offs will you truly understand why choosing IPVS over iptables matters at scale.
That deep interaction with the system mapping, reproducing, and measuring is the fastest route to achieving true mental mastery over Kubernetes networking.
Thank you for joining us on this deep dive.
We hope that the next time you see a connection timeout, you won't feel confusion, but a clear, structured list of 5 places to look.
Until next time, keep digging deep.